So what we have here today needs no new introduction. This is the famous Gaussian integral, and this is a more generalized form because in the original one the value of a just equals to 1. So at first let's talk about the history of this integral. This integral was first published by Abraham de Moivre in the late 1800s. De Moivre is the same person on whose name is the De Moivre's theorem in complex numbers. And later on, after some years, Carl Friedrich Gauss proved it and gave the value for it. From there itself, it is known as the Gaussian integral or the Gaussian integral. And that's with the history part. Now let's start with the maths of it. So I will not be using polar coordinates or double integral for solving this problem. I will be just using simple multivariable calculus for solving this. So let's begin. So at first, what we should note is that the function here is an even function. Means when we put minus x in place of this x, we get the same function back. And also this integral is a full range integral, which means that this runs from minus a to plus a. So by the property of definite integration, we can write this equals to nothing but 2 times of integration of 0 to infinity of e to the power minus ax square times dx. Let's call these integrals to be I. Now we will define a new function, say j. This will be a function of t which equals to integration from 0 to t of e to the power minus ax square dx, but it's whole square. Now this step is called parameterization. So we will be working on this j of t, and at last we will be finding the value of I with the help of this j of t. So what we will do at first is we will differentiate this j of t with respect to t. So for that we will be needing the full of Leibniz rule because the limits are not independent of t. So I am writing Leibniz theorem here for those who do not know what is Leibniz theorem. The Leibniz theorem says that when we differentiate with respect to t, an integral running from alpha of t to beta of t, that is two functions of t, and the inside function is both of x and t times dx. This equals to, the first term is just interchanging this integral with this differential sign and converting it into a partial derivative. So we have integration from alpha of t to beta of t, partial derivative with respect to t of f of x comma t dx, and then we will have the second term, that is putting this upper limit in place of x. So f of beta comma t multiplied by the derivative of this upper limit with respect to t. So nothing but beta prime of t minus the same thing with the lower limit, that is f of alpha comma t times alpha prime of t. This is the full Leibniz theorem. So now we need to differentiate this function with respect to t. So what we have is dj dt equals to, this 2 will come in front, so we have 2 times integration from 0 to t of e to the power minus ax square times dx multiplied by the differentiation of this integral, that is for the chain rule. Now for doing that we will be needing all these 3 terms. So the first term will be integration from 0 to t of partial derivative with respect to t of the function inside, that is del t of e to the power minus a times x square times dx. Now as you can see that the function inside has nothing to do with t, so in the t world x is just a constant, so this whole term becomes 0. Then we have putting the upper limit, that is t, in place of this x, we have e to the power minus a t square then the derivative of the upper limit with respect to t, which is nothing but ddt of t, which is just 1, minus putting 0 in place of this x e to the power 0 times we have d0 dt, and which is just 0. So this term is also nothing but 0. So what we are left with is this. We have 2 times integration from 0 to t of this e to the power minus x square times this e to the power minus at square, which is nothing but e to the power minus ax square plus t square by the property of exponents times dx. Now, how can we do this integration? So at first, let's take this t square common from here, from this bracket. So we will have 2 times integration from 0 to t of e to the power minus a t square times x square over t square plus 1 times dx. Now we will do an u sum. We will put u equals to x over t. Then we will have t du equals dx. Taking this t on this side and then differentiating with respect to nothing, with respect to ar, we have t du equals to dx. So converting this whole integral in terms of this t and u, we have integration, putting this lower limit 0 in place of this x, we have u equals to 0 over t, that is just 0, and putting this t in place of x, we have t by t is just 1, so u equals to 1, and then we have this 2, so 2 e to the power minus a t square times u square plus 1, and dx means just t du, so we have t du, and on the left hand side we have dj dt. Now I want you guys to note something. The limits have become free of t, and what we are trying to reach is this g of t, and we are in a stage of dj dt. So summing up all this, what we need to do is we need to integrate this function to return to this j. But before that, what we need to see is that the limits have become independent of t. So we should think of the special case of Leibniz theorem, which says that if the limits of integration are free of t, and we can write the function inside here as some derivative with respect to t, then we can just swap the integral with this differential sign and convert that partial derivative into an actual derivative. I know it might sound complex, but when I write it will be crystal clear. So let's clear the board so that we can have some space for calculation. So what we have is this. Now we are trying to write this function as derivative of some other function with respect to t. So what I mean is, this function is nothing but ddt of minus e to the power minus a t square times u square plus 1 over a times u square plus 1. When we differentiate this e to the power something with respect to t, we have this e to the power something, and then by chain rule we have this minus 2at times u square plus 1. The minus minus becomes plus, and a times u square plus 1 gets cancelled, and we are just left with 2t. And here also we have this 2t and this e to the power something. So this thing is just equivalent to this thing. They are nothing different. I am just writing this function in this form. So what we have is dj dt equals to integration from 0 to 1 partial derivative with respect to t minus a t square times u square plus 1 over a times u square plus 1, and we have this du, and yes, it is alright. So I want you to note that these two are nothing different. These two are the exact same things, just written in another form, another fancy way. So by the special case of Leibniz theorem, or the reverse of Leibniz theorem, what we can do is we can just interchange this differential with this integral, since the limits are free of t, and then convert this partial derivative into an actual derivative. So we can write this thing as d dt of integration from 0 to 1 of this whole thing is e to the power minus a t square times u square plus 1 over a times u square plus 1 times du. Sorry, another bracket. No. I hope it is alright. Yes. Now, this is nothing but dj dt. Now, something strange will happen. We cannot just cancel this dt with this dt, but that is something that happens. That is something that just holds. It happens always, and it has always happened, and till date there has been no exception to this. So we can just cancel this dt with this dt. You can just feel it in that way, and we can write this dj equals to this d of this whole big integration. Now what we have here is a differential equation. Now we can just integrate both sides to solve for it. So integrating both sides, we have this j equals to this whole integration, that is integration from 0 to 1 of minus e to the power minus a t square times u square plus 1 over a times u square plus 1 times du, and of course the plus c. Now we have an extra constant c, and we have no boundary conditions for solving it, but as always we will generate some by our own. So let's make up some space. So now we have cleared the board, and our next target is finding the value of this c. So for finding the value of this c, we need to write this actual function here. So I'm writing the function, that is integration from 0 to t of e to the power minus a x square tx and its whole square. This is just j of t, and this is also j of t, so these three are just equal. So what we can try is we can put the value of t to be 0. When we put the value of t equals to 0, we have integration from 0 to 0, and by the property of definite integration, integration from a to a is just 0. So on the right hand side we have just 0, and on the left hand side we have putting 0 in place of this t. This becomes e to the power 0, that is just 1, and minus 1 over a is just constant, so taking minus 1 over a, we have integration from 0 to 1 of this du over u square plus 1 plus c. Now what is this? This is just tan inverse or arctan. So it becomes, implies 1 minus 1 over a times tan inverse u, because u is the variable here, and the limits are from 0 to 1, plus c equals to 0. Now this is nothing but minus 1 over a. Tan inverse 1 is just pi over 4, so pi over 4. Tan inverse 0 is just 0, so not writing that. We have this. So this means c is nothing but pi over 4a, and that's done. C is the only thing we required for finding the function j of t. So writing this value of c here, we have this j of t equals this function, this integration, plus pi over 4a. So clearing the board again, we have cleared the board and we have the function that is g of t. We also know the value of this c. So only the last step remains. Now for finding the value of I, what we need is the relation between this j and I. So from these two we can clearly see that I is nothing but 2 times root over j when t tends to infinity. I hope this is pretty simple, this is pretty clear. Now for this j when t tends to infinity, we have, putting infinity in place of this t, we have e to the power minus infinity square, which is just 0, because the graph of e to the power minus x is somewhat like this. The x-axis is an asymptote to this curve and it cuts at 0, 1. So when x approaches infinity, this y approaches 0. So this whole thing becomes just 0 and we have this pi over 4a. Now for the value of this I, we have I equals 2 times root over of this whole thing, that is just pi over 4a, which is nothing but root pi over a, and that's done. So the answer to this integral is just root pi over a, and in the original one the value of a just equals to 1, so the answer is just root pi.
One eternity later.
So what I want you guys to note is that the original function was a function of e and the result is a function of pi. Isn't that amazing? I always had this question in my mind, that what is the actual connection between this e and this pi? And I always had this feeling that they have something to do with nature. They have some deeper physical significance which we are yet to perceive. Modern day string theorists are working on this, that why this pi, this e occur at these exact numbers. I mean, why the value of this pi is 3.14159 and etc. and not something else. They say that this has got something to do with vibrations, with some frequencies and sounds that happen all around the universe, in the cosmos. And this idea amazes me a lot, because I also feel they have some meaning in nature, they have some physical significance. They are not just irrational random digits put together, but they are something beyond this 2D world. So this is a mystery. And also in some sums like this e and this pi occur together. This is a bigger mystery because they are totally different in their definitions, in their digits, but still there is some beautiful connection within them. They are somewhat intertwined with each other, and in the Euler's identity, that is e to the power I pi equals to -1, there is some beautiful link which we are yet to perceive. There is some beautiful symmetry in their asymmetry. And I want to end this video on this note, that not everything requires symmetry. Some things are beautiful asymmetrical. That's it. The solution I showed in this video, I was inspired from 2 of Dr. Peyam's videos and 1 of Flammable Maths, that is Papa Flemy's videos. Dr. Peyam has got nearly 14 different ways for solving this Gaussian integral. You should check those out. Those are just magnificent. And that's all. I hope you liked the solution. I hope you learned something new. Thanks a lot for watching. Have a nice day. Signing off.
One eternity later.
This pi is not just the ratio of the circumference to the diameter of a circle. This pi is much more beyond it. This pi appears in places in physics and maths where there is no connection to any kind of circles. For example, in this series is 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus dot 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 up to infinity. This results in just pi over 4. I mean, how and why? Yes, I might know the proof, but I am talking of the physical significance. Why does this happen? this pi is a very mysterious number, and so let's end this video with a joke. When it comes to pi, I get emotional. Bye bye.